Abdulaziz Khan with you, and in this lecture we will go through some idea of propagation under atmospheric influence. However, before that, as I want to keep a kind of momentum and I want to link the video so that I will try sometimes something which is given in one lecture, it should be kind of shown in the next lecture. Like if you remember, our previous lecture was about the FRIIS equation, and I took you to this FRIIS equation, and we say that the received power is equal to transmit power plus gain of trans antenna, gain of receive antenna, and then this is minus basically. This is inverse of free space loss, so that is why this thing will become minus as a free space loss. It is plus because these values are in inverse. So as I told you last time also that I won't go in a lot of mathematical detail, but this is simply, I will show you that how it is minus. So let me show you a small Excel file. I hope you can see that. I have made it on Excel and I will show you this same on Pathloss so that we can, what I was discussing is that we will try to show you exactly that if something is in Pathloss, then how it is actually calculated so that you have a bit of idea. And let me try to explain also that why for a good planner it is necessary to know. You can say that I have the tool and the tool tells me everything, so why do I need to know? Basically what happens when you are sitting somewhere, there's a long discussion going on. If you have some idea, like if you know that how the gain effect, how the frequency effect, how the wavelength effect, how everything affects a link, if you have some background idea, then for you it's a bit easy. So we will see a path loss of a link budget of a link, and then I will correlate this. Just assume, like in our last lecture also, we found that the free space loss was going to be something like 132.51. This is atmospheric absorption loss. This is calculated by Pathloss. But I have just put the value because this value is used. So I will make a link. The transmit power of the radio should be plus 26.5, and I have both the same antennas. So 40.8 and 40.8 is the gain. So if how it is done is that you add the transmit power and antenna gain 1, antenna gain 2, and then you subtract from it the free space loss and this atmospheric, because this is also a loss. These two are losses, so they are subtracted. So you get a received power value which comes to be minus 24.6. Also on path loss you will see there is a net path loss value. Net path loss value is basically because you have a path loss of 132.51 plus 0.15, almost 132.66. If you add these two, it will be 132.66. So you remove these two gains from it, 40.8 and 40.8. So you get this 51. 51 is the net path loss. It means that this is the loss that will be incorporated. So whatever you want as a receive, you can adjust it through the transmit power. For example, if you want a bit lower receive value, then you can decrease this transmit power. So this value will become more negative. So let me show you both these on the path loss screen. If you are following this up, this was a link that I created. I have already made a small plan of the link. So if you see here, you will see that the net path loss is 51.07. it's almost same. I mean, I calculate 51.06. There may be a very small difference. How it is that it comes 51? Because you see these antennas. The antenna gain is written here usually. So the antenna has a 40.8 gain. Same is here also. The antenna has 40.8 gain. So as I showed you here, these are two antennas, 48.08, and this is the free space loss. So we get the net path loss of 51.06. And the receive signal, because you see here we have a transmit TX power of 26.5. Same that I write here, 26.5. So 26.5 TX give me a Rx of 20 minus 24.56, which is almost the same, minus 24.57. I mean, there is some difference of only 0.01, which is negligible. So let me take you one step further also. I mean, it has calculated a thermal fade margin of 65 dBs. From where it comes from this, the threshold. As the threshold is minus 90, so you make a difference of the received signal and the threshold, so you get a fade margin value. So I hope that you should be getting something out of it. My point is that I want you to have some background idea that how the number that we see on the path loss screen, how they are actually calculated. If you have any question about it, then you can comment and I will be very happy to guide you. So that was, you can say, that was part of the previous lecture. In previous lecture we studied the FRIIS equation, and then I showed you that how the FRIIS equation is used in path loss and how my values in Excel were the same as the values in path loss. So let's start our lecture number 9, and let me go through this. So microwave propagation under the influence of atmosphere. So basically the radio wave that microwave frequency behave like light wave. So it behave almost like light wave. So there are certain optical principles in describing radio wave propagation, because from the light we know that the light reflects, diffracts or refracts. So the microwave also does all the same things. And when we send a microwave from one point, at the receiver, it goes through the same under the influence of atmosphere, it goes through the same principles of light wave. I mean, because of the atmosphere, there is reflection, diffraction, and refraction, everything. And that we will try to learn in the coming lessons. And but the reliability of the system, it depends a lot on the atmospheric condition. I mean, then if there is rain, we will see that how rain and snow or uh, anything makes the same kind of problem for microwave that we can see usually with light wave. So video, I have just type of introduce you that now we will start learning about the deep things like the microwave propagation and its atmospheric influence on this propagation. So see you in my next video. Goodbye.